So in the last video we talked about why we need length contraction, or what goes wrong when we're considering comparing velocities if we take account of time dilation without bothering with the length contraction. But the kind of good news is, if we understand how time is dilated, we can work out how length has to be contracted to cancel out the skewing, such that overall, everyone agrees on the velocity, for example, a spaceship is moving at. And this idea of length contraction might actually one day help us travel, to distant galaxies, travel to, the centre of our own galaxy, or at least, travel stellar distances, thanks to the phenomenon of length contraction. Which would be pretty cool. I mean, in the Star Wars universe, there's lots of really cool things in the part of the galaxy that's called the Deep Core, where you have, for example, the Maw, with kind of a very interesting creature called Abeloth in the heart of the Maw. Our centre of our own galaxy doesn't have Abeloth in it, mercifully, but it has Sagittarius A star, a massive black hole, and so being able to travel, around our galaxy or to other galaxies would be really cool, and length contraction might just give us a way to do it, and reach distances which are, far greater than, even 100 light years away within our own lifetime, without, rather miraculously, breaking the speed of light limit. So let's remind ourselves a little bit about what we saw in the last video, and I'll put a link below this video if you haven't seen the last one. I would recommend checking the last one out, but it's not completely necessary. For this video, the core thing is, if we have, let's say, a spaceship, let's say, for example, Captain Picard is on, the Star Trek ship, and that ship is, travelling away from Earth, the velocity of that ship should be the same according to the captain on board that ship, so according to Jean-Luc Picard, as it would be for someone stationary on Earth watching that ship fly away. In short, we require V prime and V to be the same, where in my last video I had V prime be the velocity of the ship relative to the Earth, and V be the velocity people on the ship believe that the ship is, travelling at, or equivalently, V is like the speed at which Earth appears to be moving away from them. And we require that V prime equals V to not run into a few contradictions. But thanks to time dilation, this calls this into question, but we can cancel out the fact of time dilation by having length contracted by the sine factor that time is dilated, such that the two effects will cancel out and V prime and V will be equivalent. And so for this, we're considering a situation where we've got, Earth, which is kind of like, well, in its own reference frame stationary, and it's receiving kind of signals from a rocket. And the speed that people on the Earth believe the rocket is moving away would equal the distance a rocket seems to be travelling, so ds divided by dt prime. Now it's dt prime because the signals that the rocket are sending to us to tell Earth where it is are time dilated. So it's dt prime instead of dt. Now, for people on our ship, be that our rocket or our spaceship, according to them, there's no time dilation with the signals they're sending, because the signal box is co-moving with the ship, so it's stationary relative to the ship. So there's no time dilation there. However, since the ship is moving through space, if we look at a reference frame where the ship is stationary, the space around the ship seems to be moving, in which case we would have some shift in the kind of distance between 2 points, some kind of contraction along the spatial axis, causing the distance between 2 points to be ds prime rather than ds. And here, for this video, I'm using s to refer to spatial distances, not the space-time interval, worth just emphasising for this video. So now we'll talk a little bit about length contraction and what length contraction is. Let's get an equation to describe this. And we're going to get the equation by using the idea that length contraction has to cancel out the effects of time dilation to ensure that people agree on the velocities an object is moving at. Now we know from what we've said, since time is dilated, the length has to be contracted, and length contraction happens, in the direction or along the axis that an object is moving. But essentially, it's squished along that axis. And if we want an equation for it, we remember that we're trying to say that ds prime by dt, so that is the velocity which the spaceship would think it's moving at, compared to the surroundings, must equal ds by dt prime, so the speed the spaceship is moving at away from Earth, from the perspective of people on Earth. And just doing a bit of a rearrangement, we can end up with this fraction, and I've done that because we know how dt prime and dt relate from previous videos. Now dt prime is the kind of dilated time, so that's gamma dt, so we can conclude that ds prime by ds would have to be 1 over gamma, because the dt's will cancel out once we substitute that once we substitute that dt prime is the same as gamma dt. And rearranging just a tad, we get to ds prime is ds over gamma. Now gamma is 1 when v is 0 and approaches infinity as v goes to c. So in other words, as an object starts moving very, very quickly, it will seem to be compressed from the perspective of people looking at it, or if you're on the object that's moving, the space around you will seem to be compressed. And the new length is given by dividing the old length, so the length when we're not worrying about motion, by the Lorentz factor gamma. So as we said, the overall effect is that things essentially squish along the direction of motion. And let's have a go at working out at what speed is required to achieve a particular squish, if you like, to make this more concrete. So let's say we want something, let's say we've got a spaceship and it's flying away, and we want to find the velocity at which the length of the ship will appear to be half of the length it was when it was just sitting stationary on its pad, if we were looking up at the ship. Well, we have that ds prime would be a half times ds. and we can, use the relationship between ds prime and ds to then get that gamma would have to equal 2, so our Lorentz factor is 2. And then if we remember the definition for our Lorentz factor, where c is the speed of light and v is the velocity the spaceship is moving at away from Earth, then we end up that the spaceship would have to move at about 0.87 times the speed of light to achieve this kind of a length contraction, which I think is in many ways really pretty cool. So now we talked a little bit about what length contraction is and gone through the major possible future advantages of using it briefly at the beginning of this video. Let's just kind of recap why this length contraction stuff, despite being very abstract, is useful. So for this, kind of, if we think about you on a spaceship, which is travelling away from Earth, well, according to people on Earth, the spaceship is the thing that is moving. And so they see the length of the spaceship contracted along the direction of its motion. However, if you're on the spaceship, and to a good approximation, even if you're moving around on the spaceship, providing you're doing it at a speed much less than the speed of light, then you are stationary relative to the spaceship. So if you're on the spaceship, according to you, the spaceship is completely stationary. Instead, it's the Earth and the other things around space which are moving relative to you and the spaceship. So it's those things that are moving. So you see distances between those things being length contracted. And the quicker your spaceship is travelling from the perspective of Earth, the more length contraction you will see. And you can make length contraction, as significant as you like, because as the speed of the ship approaches the speed of light, gamma approaches infinity, and ds prime will therefore approach 0. So you can make distances between objects as small as you like by travelling at a significant enough velocity. So you could get to the centre of the galaxy manageably in a day using length contraction if we ignore other facts like whether the body can endure such speeds and all the other complexities. And so this is really quite cool, and length contraction could help us travel the cosmos. If you wanted to get to the centre of a galaxy in a day, you can do that. If you want to get to the edge of the observable universe in a day, at least if we ignore the expansion of the universe, you can do that. But whilst it's usually large velocities where length contraction is noticeable, it can have important indirect effects for objects moving at a low velocity. So, for example, if we consider a wire with low resistance, we can model the flow of current through that wire, at least direct current, as electrons moving uniformly, nice and neatly in a single direction at a steady speed. However, when we look at moving charge, we see something very strange. Now, from the perspective of the moving charge, nothing strange is happening. The charge is generating an electric field, and that's all that's really going on. However, because the charge is moving, it does perceive the wire being a little bit shorter than the length you think the wire has as you're watching electrons go across it. And this tiny difference in views about the length of wire, and also associated tiny differences in the passage of time, means that you actually perceive the electrons causing a magnetic field, even though from their perspective they just think there's an electric field. And so the fact that you moving the fact of length contraction means that we get a magnetic field in the first place. And also because a magnetic field arises from time dilation and length contraction effects on an electric field, a magnetic field is really a kind of like a relativistic shifted electric field. Which again is why in the context of full electromagnetism we just talk about the electromagnetic field. It isn't really possible in the full context of electromagnetism to split up an electric and magnetic field. And because this, the kind of production of a magnetic field is relativistic, and you get a strong magnetic field when particles have a lot of energy and are so moving very quickly. We say that the electric and magnetic fields become, more deeply coupled at higher energies. And we see this unification of forces at higher energies in other contexts as well in particle physics, which I won't go into in this video to keep this video of a manageable length. But I think length contraction is pretty cool in a lot of ways. But now we have a feel for length contraction, let's go on to compare the velocity you would actually need to travel at to get from one point to another if we take into account relativity, with the velocity you might think something would need to travel if we use good old Euclidean geometry and we don't worry about any relativistic effects. So we can compare, how significant this length contraction actually is. So we want to find an expression which will give us one, how quickly we would think a ship would have to move to, let's say, reach the centre of a galaxy in a day, to how quickly it would actually have to move if we take into account the very helpful effects of special relativity. At least helpful in the sense that length contraction means we can travel a lot further than we could otherwise. Now, if we're going to get the speeds, we need to also have the distances. So let's look at comparing the distances. Well, the distances are related just by our length contraction equation, where delta S is the distance, say for example, between Earth and the centre of the galaxy. Now, Earth and the solar system generally doesn't have significant radial motion relative to the centre of the galaxy. That is, it's not moving really towards or away from the galaxy. From the centre of the galaxy, it's more just moving around the galaxy. So delta S being the distance from a stationary reference frame, that could be the distance from Earth to the centre of the galaxy from the perspective of Earth. At least when we say distance, we mean the radial distance. If we're not talking about radial distances, then the Earth wouldn't be a particularly good stationary reference frame for that. But to make matters simple, let's assume we want to send our ship directly towards the centre of the galaxy, so we want to send it radially anyway. Well, then the distance the ship thinks it would need to cover would actually be delta S prime, which is length contracted. So it's less than delta S. And to get a velocity from that, we can recall the equation between distance and velocity. So we know distance is equal to velocity times the time interval. But because we're dealing with special relativity, we have to be very, very careful what time interval we're using. We don't have to worry about about the velocity, because v and v prime are the same. That is, the speed that the ship would be moving at away from Earth matches the speed the Earth would move away from the ship if the ship was to start moving. And so v prime and v are the same. And in fact, we derived length contraction to ensure that they would be the same. So we don't have to worry about what v we're picking. The speed the ship will move at is the speed the ship will move at. If somebody looks outside of the ship and looks at stuff around them, they will determine that the ship is moving at the same speed that somebody on Earth would see the ship moving away. But what we do have to worry about is the time interval. Now, if you're on the ship and you're looking at how time is passing to allow you to determine the speed that the ship must be moving at relative to everything else around it, well, if you're on the ship and you're looking at a clock on the ship, assuming that clock isn't moving around the ship at near the speed of light, that clock is pretty much stationary relative to the ship, so there is no time dilation actually occurring for you as a crew member looking at that clock. So we can use delta t. We don't want to use delta t prime, because delta t prime would be the dilated time, so the time that is that the clock would seem to be moving at if you were looking at it all the way from Earth. I mean, you would need a very powerful telescope to do that, but in principle you could. And so the velocity the ship would actually need to move at to cover the distance would be equal to ds prime divided by, would equal delta s prime divided by delta t. However, the distance a stationary observer, that's on Earth, might think that the distance, the ship would need to travel would be delta s, so the distance is according to Earth, divided by delta t. And I put delta t because, we're talking about how quickly the ship would have to travel. We're not talking about how quickly the ship seems to be travelling once it starts travelling from the perspective of the Earth. So when we're talking about how quickly the ship would have to travel, again, there's no time dilation really going on. Because if you sit down in a board meeting talking about how quickly a ship would have to travel, you're not going to be using clocks with measuring time at different rates, so we don't have to worry about time dilation there either. And to summarise, because I know that's a lot of stuff I've just said, K is a symbol I use for delta S over delta T, and that represents how quickly you would think the ship would have to travel if you were in a board meeting discussing, designing the ship and seeing where it could get to. But we're assuming there that we're not worrying about relativity. So this is just the standard, look on Google for the distance to the heart of the galaxy, and divide that by how long you would want the ship to take to get there, and that will give you the distance you would think the ship would have, and that will give you the velocity you would think that the ship would have to travel at. However, if we want to compare v with k, you can use the fact that we define k to equal delta s over delta t, and we've derived that delta s over delta t is v gamma to get that v, where v is the velocity the ship would actually have to travel if we take account of Lorentz, length contraction, would relate to k via our top equation in our right-hand box. So v represents how quickly the object or spaceship would actually have to travel. And it's worth checking whether this equation makes sense. So, there are different kind of checks you can do, but for very small velocities, k over c is going to be tiny, so v squared is about k squared, so v and k would agree. So the distance, the speed the ship would actually have to travel closely matches to how quickly you would think it would have to travel if you were to ignore special relativity. However, an interesting thing is that no matter how large k is, so no matter how quickly you would think the ship would have to travel if you were to ignore relativity, there's actually a speed v less than the speed of light that this relates to, which tells you how quickly the ship would actually need to travel. So it doesn't matter how quickly it looks like something would have to travel to get to somewhere. There's actually a velocity less than the speed of light where that could be accomplished if we take into account relativity. So let's have a go actually calculating how quickly something would need to travel in reality if we take account of length contraction to get to the heart of our Milky Way galaxy. Now our galaxy is quite big, to say the least, really. We're not completely on the outskirts, but we're a fair way from the centre. If we look at where we are on the spiral arm, we've kind of engulfed it. And it turns out we're about 20,000 light years from the centre of our galaxy. Now, before looking at this video or hearing about length contraction, you might have thought, well, 20,000 light years would mean that, if we could travel at the speed of light, which we can't, it would take 20,000 years to get there, well beyond the human lifespan, so, no way we're ever going to do that. However, thanks to length contraction, if you want to get to the centre of the galaxy today, well, once we invent things that can travel fast enough, that can be managed. And we don't require those things to go faster than the speed of light. Now, it's worth saying your reference frame, if you're moving, you are not exceeding the speed of light because the distances are contracted, so you're still moving slower than the speed of light despite reaching the centre of the galaxy. It's just from your perspective, the galaxy is going to be a lot closer than the centre will be a lot closer than 20,000 light years away. Well, we can use our equation we had on the last slide, which relates v and k. Now, from the information we've been given in the question, we can work out what k would be. K would be how quickly we would think something would have to travel intuitively. So, ignoring the effects of relativity, v will be the speed it will actually need to travel, and we can rearrange our equation into this form here, which will be slightly more helpful, particularly when k is much larger than the speed of light. The bottom equation is going to be much more useful, as we'll see. But anyway, let's have a go at working out what k is. So k is going to be a distance of 20,000 light years, but in meters, and 1 light year is about 9.5 times 10 to the 15 meters. So that's where we got that number from, and we divide it by the how long the day is, and because this is physics, we always measure time in seconds. So the number of seconds will be 24 times 60 squared. And when you go through that, you end up essentially with this. You've got that k would have to be 2.19 times 10 to the 15 meters per second. So we would conclude that something would have to travel a lot faster than the speed of light intuitively to reach the centre of our galaxy, but thankfully that's not the case. Now, because k is so large, if we want to find the speed something would actually have to travel, we have to make use of the binomial theorem, because if you put c divided by k into your calculator and run through everything, because c divided by k is going to be so tiny, your calculator will end up telling you that our object will actually travel at the speed of light. Now, it won't. It's just that v squared and c squared are going to be very similar because c over k is tiny. And to work out the difference, it's actually helpful to use the binomial theorem. So if we use the binomial theorem, which we can do, we look at, v squared is equal to c squared divided by 1 plus c divided by k all squared. Because c divided by k is tiny compared to 1, we can use the binomial theorem. And when you do that, you'll end up with v squared is about c squared, lots of 1 minus c over k squared. And that gives you that v is about c multiplied by the square root of 1 minus 1.88 times 10 to the minus 14. So it's very close to the speed of light, but importantly it is below the speed of light, so we would only need to give our ship a finite amount of energy for it to accomplish this, so it is possible, which I think is really cool. So we talked a little bit about length contraction. I don't know whether I'm going to do a video about full-on velocity addition, because that's cool in relativity as well, and would build upon the last few videos neatly. The reason I'm not sure if I'm going to do it is because I don't like doing videos unless I can talk about some kind of cool application, and I don't really know of a good application of relativistic addition of velocities. I could come up with fairly trivial ones, but hopefully I'll find something which would be a good example, even if it's on Star Trek. But anyway, that's everything for this video. I hope it's been enjoyable. I hope you're relieved to know that we might be able to travel the stars one day, thanks to length contraction, and wishing you all the best and a very good start to the Advent season. And don't forget to have a few good mince pies as well, and hopefully see you for some more wonderful physics soon.